My talk is a little bit, it clashes a little bit with the previous talk by David. Well, not so much because it is going to be a little bit more practical. Suited for traditional relational databases. Then we'll go a brief overview of Redis itself. Then we try to devise a moderately general procedure to convert a simple PostgreSQL schema to Redis. And then we'll see what is going to happen after we do that. Afterwards, we will discuss a little bit when you shouldn't really use Redis, when you should stick to something else, relational databases. And as a bonus, if we have enough time, well, this is a long talk, so we'll probably have enough time, I'm going to talk a little bit about using Redis as a message bus. So, to keep it practical, we've had an indexing of DHCP leases application. Basically, we had a DHCP daemon which was producing, which was putting all the information about leases it creates and hands out to syslog. And then there was this little indexer daemon which put this information in a nice form into the relational database. And then via an API, there were multiple programs querying that information for various reasons. And since we are not a particularly small shop, I work for the Danish branch of TIDA, which is a Swedish token. So we have a substantial number of leases. And at some point, this scheme using Postgres database, which is what we used for putting stuff into the database, basically we encountered quite substantial performance problems. So the database was really simple, right? Because it had to be really performant. So we are not talking about 25 tables with 50 indexes and stuff like that. So it was really, really, really basic. Basically, we had a single table with the following columns in it. Of course, we had to store the IP address and the circuit number, which is sort of a custom identifier of some kind. And then the start time and stop time of particular lease, the MAC address of the device which got the lease, and a couple of service information, because this particular database was indexing, in addition to normal internet customers, also VoIP and Internet TV and stuff like that. Right, and I already gave this talk once, a couple of months ago at the Nordic Code Workshop in Malmö, and people who are really Postgres professionals mentioned that, oh, but you could have done this table much more efficiently. For example, you could have used the built-in internet IP address data type and basically save, instead of using 15 characters, you would use 4 bytes or 8 bytes, whatever. And you could have used the traditional date time data type, which is probably also a little bit more efficient than the Unix one, although it's debit and stuff like that. But it doesn't really matter, because the kind of performance problems which we've got, they could only postpone it a little bit, but never entirely eliminate with this solution. So the syslog events, the syslog lines which HTTP server produced look like that. I split it up a little bit into separate lines, but again, it's pretty basic. So the IP address of release and the circuit number, which is a custom identifier, duration, and all the other fields which would basically just insert in the database. And in our setup, we have about 100 lines like that a second. So and one line of, to process one line of this log like that basically involves the following. So first of all, we validate the line and see whether it is actually valid Redis allocation or whether it's something else, in which case we just ignore it. And if it is the valid one, then we immediately go to the database and fetch the latest keys given out on that particular IP address, right? If there was no such list at all, then it is something new and we don't care about anything, we just blindly insert the entry into the database, right? If we found it, then we see whether it corresponds to the same customer and whether it corresponds to the same device. And if it is the case, then we verify whether this latest list for that IP, for the same customer with the same MAC address, whether it actually expired. Because if it expired, then we need to still insert a new one. So if it didn't expire, we just update the stop time, which will be, again, another half an hour in the future or some such. Otherwise, if it's not the same customer, if it's not the same MAC address, again, we see basically if the latest one at that IP address, whether it needs an expiration forcefully. If not, if it's already expired by itself, then we just insert. Otherwise, we have to update the stop time of the latest list with that IP, and after that insert a new one, so that we never have a situation when with overlapping time intervals with the same IP address list. So it's pretty basic. But if we count the database accesses here, we can see that we always have at least one fetch here, at least one select. And either we have two updates, or rather one update and one insert, right? Or just a single update. So in the best situation, we have one select and one update. In the worst situation, we have one select, one update, and one insert. Yes?
Just querying your choice of model here, why not just insert everything as it comes in, and then when you actually need to look something up, fetch all the records that could match that time period and choose the most recently created of them?
Well, two reasons. The first reason is that we will have even more records in the database, and therefore we will have even more performance problems, because
but it's pure inserts. You're not doing all the lookups anymore at insert time.
Yes, but we are still doing the lookups on the API side, right? When they actually ask who had that IP at that time.
Yeah, so you get back maybe 5 records instead of 1, and then you're only processing 5 records to work out.
But the thing is that the more records you have, basically the shittier your database accesses become. But it might not be particularly important. The second reason is that we cannot allow to have the same IP to be allocated to several different customers, right? So we have to put this cut lines in. Yeah. So meaning that if we do that, then we have to do the fetch. And if we do the fetch, then it is actually cheaper and easier to do the update rather than inserting everything. Right. Okay, so the workflow is pretty simple and basic. Now those API requests, when we actually ask who had that IP at that time, you don't have nearly as many of those, about 2 per second on average. Sometimes it comes in bursts, sometimes nothing happens for a little bit, but on average, 2 per second. And we do several possible requests. For example, which customer has this ID right now? What IP has this customer now? And the information about the history, like who had this IP 1 month ago for 2 days, stuff like that. And the same about the customer information. The customer with this ID, with this server number, which IP addresses he had over time. The majority of requests are actually about this IP right now, so the cheap ones. The requirement for the queries is no significant processing delay, meaning that we basically try to eliminate the lying part. We try to eliminate as much as possible the situation when another customer got this IP, but the query is done for this IP at the second, and we still reply the whole customer. So, meaning that those updates should actually go into the database as fast as possible. And little delays are fine, but significant delays can actually lead to bad things with regard to provisioning of network elements and stuff like that. Yes?
No.
Right. Just as I said, we have from 2 to 3 database operations, and on just a normal Unix server, which is not particularly powerful, this kind of performance unfortunately becomes a problem. Especially when we try to do some other stuff on the server, like periodic vacuuming of the database, because we also clean up the old pieces. Basically, we never store anything from using it here, because basically we are not supposed to keep this data. Right? So, and as soon as you try to do Postgres vacuuming, then basically everything halts and slows down quite a bit. Eventually, you will still get the data into the database, but delays would become actually unacceptable. So, what are the possible solutions to this performance problem? One solution is to do some database optimization, basically making schema a bit smarter, as I was suggested, changing the data types and maybe doing something else. Maybe some indexing, but we already had all the indices which actually mattered. We could also try to do some black magic. I believe Postgres has like more than 250 tunable parameters, and some of them might have probably helped this situation, maybe. I don't know. Then, of course, we could do some clustering, do some vertical division of data, so that this range of IPs is handled by one Postgres server, and the other range is handled by the other. Of course, we could probably buy some really expensive hardware and scale 3-4 times faster than we had. The same for Oracle. It typically runs on a pretty good hardware. Again, not that it is faster than Postgres for this simple task, probably. Almost definitely not. Anyway. So, and finally, we could use one of the NoSQL solutions, because the schema is so simple. I mean, they don't really need relational database for this. That's great, because there are no relations. It's a simple thing. So, and then the question is, which one of those NoSQL things to choose? And we have plenty to choose from, including those, but I don't think that's all anymore, I think. So, and this talk is about one particular solution, which is Redis. Here is the website of Redis, redis.io. It supports several complex data. I mean, in the end, it is just a key value store. So you have a key and you have the values, but it is a little bit smarter than that. It actually supports several different data types underneath the keys. So it supports the normal strings, which you would expect from memcached or DB file or whatever. But it also supports some hashes, lists, sets, and sorted sets. It has a very simple text-based protocol. There is a command line client, but telnet will work just fine as well if you just squint a little bit so that you ignore the dollar sign and stuff like that, then you operate telnet with Redis. And its application domain is, according to one review of different possibilities of NoSQL, is for rapidly changing data with a foreseeable database size, which fits most of them. Right? And in our case, it is a perfect match, really, because we have pretty rapidly changing data. And we do have a foreseeable database size because we have a really good idea how many customers we have and how often they actually ask for new IP addresses. So at least it is bounded from the above pretty well. So on cpan, there are several modules to work with Redis. And David talked about some of them. The simplest probably and the oldest definitely one is just called Redis. It is as simple as instantiating an object of Redis class. You could also specify the server and port to connect to, of course, but by default it will connect to localhost port 32000. And as you could see on my desktop machine, it is pretty fast. If you just use the normal key value without complex data types and just insert a bunch of stuff, then it's about 8 kilo inserts a second on just a normal desktop machine, which is really great. So, as I mentioned, Redis also supports, apart from the normal set key to value and get value of the key, it supports multiple data types. It supports hashes, which is in a way like a second level hash in Perl, right? Because we already have hashing when we use the keys, but also within the value we could use keys as well and values. So we have the hash set field to value, key name, field name, value, and multiple set, and verify whether the element of the hash exists, and delete and increment, stuff like that. Basically, most of the commands in Redis are pretty orthogonal to each other. So if you have set, then you will have the hash set and the set, and so on. So it just changes the first letter. The same for delete, the same for increment, and so on. Now, there are lists which are quite like Perl arrays. It is possible to access elements within a single list by index, or it is possible to do push and pop just like in Perl. So, except that Redis thinks about it as a push and pop from the left and push and pop from the right. Meaning that our push and our pop are the same as Perl push and pop, and left push and left pop is like Perl shift and punch. So, and we can get multiple elements using the least range operator. Right. Then there are simple sets to which we do add the individual elements into a set. And here we add a single red element, single blue element, and 3 greens. And when we get back the green, then of course we will have only 1 because it's a set. We can verify whether a given element is a member of the set, and we can find the number of elements, the cardinalities, S-card, set the cardinality of the set element. And we can even get a random member. Right. I'm not going to talk about sorted sets, but they're also sometimes pretty useful for various things. What about atomicity? Redis is basically a single process. So if you issue a simple one command, just addition or whatever, then it is by definition atomic, because Redis will do nothing but your particular command. What about reading value and modifying? There are some very nice special cases like increment and decrement, which are atomic again. They're extremely useful for emulating sort of sequences in traditional database speak. It is also possible to set a value of a key, but only if the key is not already there. Which is possible, by using this feature, it is possible to sort of emulate transactions by hand if need be. If all your applications are well behaving, then there's definitely one way to do transaction-like things. And then finally, in relatively recent versions of Redis, there is an explicit support for the sort of like begin transaction, end transaction, and watch this value for changes. So the transaction doesn't happen if the watched value has changed. And David actually talked more about it if you were installed. Right. As I mentioned, the increment is very useful for arranging sequences. Yeah, and while the thing was sleeping, someone else, some other process was doing increments. That's why we got 1 and 5 and not 1 and 2 instead. So working with set if not there, it's possible to do something like that. We try to set, and then we delete the lock, and do stuff in between. And otherwise we were unsuccessful trying to set the lock. So we basically go back or do nothing or repeat or whatever your application logic actually wants. So if your process which does the lock actually dies in between during the do stuff, then there is a problem because everybody else being polite will not be able to proceed. And of course the scheme could be extended with using logs which automatically expire, or with storing in the log the timestamp when the logs occur, and then if you are not successful trying to obtain the log, you could read then the value of the timestamp and verify whether timeout was reached and actually ignore the log and still proceed. So of course, by using some application logic, it is possible to implement a pretty reliable log. So yeah, the latest versions support this watch, unity, exec transaction things. David told a little bit about that, but unfortunately, at least the Redis.pm module does not support it. I'm not sure about the rest. Probably any event Redis is actually quite fine. Right. Now, the interesting feature of Redis is that it's not just, I mean, it is an in-memory store, right? But it also gives you some resistance, because otherwise, without resistance, you can just use memcached unless you need those complicated data types. Yeah, it does that. So Redis actually supports two different mechanisms for providing user persistence. It could periodically just dump the complete database state on disk, and it does it smartly. It does fork and then dump, so the operations are not quite affected, right? So you would still continue talking to it. Of course, the disk snapshot will again become a little bit obsolete, but that's one way to do it. And another way, which I personally prefer for the applications we're using Redis for, is the journaling. It has an append-only file into which it writes basically everything it does. Just append, 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 append. And if you kill the server and then start it again, it finds the file. So it reads it and basically executes all the transactions. And there is a command which you can issue right. I'm getting ahead of myself. So the normal save works and then saves the full packet. And the journaling, the problem is that the journal might get pretty large, especially if you operate on the same key over and over and over again, right? Like here, because that will be 3 lines in the journal file, and we only have we only read it from the latest 42. So it has a special command called background rewrite append only file. It's a bit cryptic here. Again, it forks and creates a new journal file into which it only dumps the most recent state, right? And then it deletes the old journal and renames the new one. The old one syncs the differences which happened before, which happened while it was writing this journal file, and then proceeds. So again, there is no interruption of service during this. And it is possible to say what it should do with regard to fsync when it writes a journal. So, and there are 3 possibilities. One is just don't do fsync at all, allow operating system to take care of that, and that's obviously a little bit of a problem if your server crashes, not just the Redis server, but the actual machine. The second possibility is to do fsync on every journal write, which basically kills the performance quite a bit. And finally, the last option is issue fsync once a second if server changes.
Do you know if your Postgres was fsyncing every single write?
Actually, I did a very bad thing with Postgres, and I disabled the fsync at some point, and it didn't help much.
Okay.
Sorry. Right. So with this 1 second fsync thingy, at worst case you will lose about 1 second. Well, if your disk actually survives, right? And it is quite tolerable for most users. Not for all the users, definitely, but for most users it's quite okay. So if this is something which you cannot live with, then probably need to find another solution and not use it. So, and this background rewrite, so that you do it as a fire and forget thing, just run it from cron every 5 minutes or whatever. And then you assure that your journal file doesn't grow too large. Right. So if you have a database such as Postgres, and we decided to go with a Redis route, I mean, that's by no means you have to just go and convert all the database from Postgres to the normal relational database, because with normal relational database, we don't really care that much what operations we perform, because it's just SQL. We could at any time add some new operations and do some selects which we didn't think about in advance, right? Here, since the underlying storage is so simple, you basically have to think about your schema. You have to think what operations you are going to do with it. It because depending on the operations, your schema depends on it. It might be entirely different if you do something else. And once you run it and once you have lots of data you manage, then it might be too late to change the schema without significant trouble, right? So the first thing we need to do is to get those operations and then design the schema around those operations, not the other way around. Then, of course, we need to make sure that it fits into main memory, because it is a main memory database. Persistence is nice, but it's only for backup. It doesn't do any operations on disk. So if your data set will fit into memory, fine. If it will not, well, either put more memory into a box or just hide it. Then decide if your current database is a production something, so you can just switch over immediately, or whether you need to have those things running in parallel for a little bit, and then of course you need to modify the code in order to support this. Right, then write code, the easy part, test, and move to production. So again, coming back to that DHCP daemon story. We could find all the SQL statements, which current scripts already do, right? What can we have? We have the indexing daemon, which does some SQL queries. Then we have the API, which has some more. Then we might have some monitoring scripts, some statistics gathering stuff, which does some other SQL. So we just basically gather them all, write them down, decide which ones should be really fast and which ones maybe don't really care about lots of function. So what operations are the bottleneck? How many times per second they executed, and so on and so on. So basically, it is pretty important to do this sort of research work. In many cases, you will just have very good guesses if it was your code which was doing the relational database stuff. But still, it's better to be thorough in this work. So in our case, remember that flowchart thing we had fetch latest, update, insert, and expire, right? So the fetch latest is simple. We just select everything from the user's database where IP is like that, ordered by the stop time of the list, and just give a single one. The update is similarly simple. We update the stop time and MAC address and the other auxiliary columns there. And we have the IP, and we have the custom identifier, and we know when the IP is actually started, so that's how we update it. And the expire latest is done just like update. It's identical signal. So, and insert is, of course, just an insert. What about the queries which API does? Well, we have what customer has this IP now, which we implement through range. Well, give me the list with everything which already started and hasn't stopped yet. Yeah. And the same for the customer identification, except we substitute the certain instead of the IP address. IP history is pretty simple, except that our range will be different. Because we actually have the start and stop times in our query. And the same for the circuit history. And periodically we delete the old stuff from this. And that's about it. That's all the queries we actually were using with Postgres for this application. So, and the following observations are that updates are much more frequent than inserts, because it is much more often when the very same device comes again and asks the server, okay, may I update this list, please, rather than the new devices. I mean, they still come sometimes, but not the majority of the allocations. And the expirations are always paired together with the inserts. And the queries, most of them are for the now and not for the history. So that's our priorities with regard to what we need to achieve speed-wise. So the history for a given IP or circuit is typically not particularly large. And the current state, as I mentioned, is changed and queried much more often than the history. And in the values for the IP addresses or circuit numbers or whatnot, we don't have spaces, like white spaces, never ever. Because, again, it doesn't matter for the Postgres, but for Redis, we have to handle the actual data format ourselves for the values. So we need some kind of encoding to find out what part of the value corresponds to. So a single IP cannot have multiple customers associated with it at any given time. While the opposite is true for a customer, because a single customer can't have multiple IPs at the same time, just easily. So we design our Redis schema in the following way. We create 4 kinds of keys. One will hold the state for an IP as it is now. Another one will hold the state, the now state for the circuit. And then we'll have the history and history for the IP and history for the circuit somewhere on the side, because that's not something which is updated very often. So the IP now, as a key, we will use this convention IP colon saying that this is actually an IP, then the IP value part of a key, and the type of a value is string, and the value itself is just a space-separated circuit, start time, stop time, service time, MAC address. Just like that. We could have used easily JSON or any other sort of encoding, but it was really overkill in this particular instance, because we know we don't have spaces, then why don't we just encode it with join and decode it with split? So the current state for a circuit is a bit more complex. We are going to use set for it, because a single customer can have multiple IPs at the same time, right? So here's a typical example when we use a set, and within that set, we are just going to use the IPs, because we can always extract the other data for a circuit, having the IP and having the timestamp. And the history for the IP is just like the IP now state, except we just do a 2-line separation of the values. So even if we have over the year a couple of thousand IP changes, so a couple of thousand records for that particular IP, it is quite manageable. It's a single stream, we just take it back, we don't do it often, and wrap within it using Perl itself. Right? So instead of introducing some complicated indices, which we could have done, of course, it turned out to be easier just to save the data and to wrap with it. So the most important key is the IP itself. And similarly for the circuit, we just have all the data there, new line separated. So now we are ready to actually implement the operations. So our flow chart still stays the same as for Postgres. We don't change the flow of the indexer at all. So we have the operation called fetch latest. And it will look like that. We get the IP, which we are going to query, and we query a key called IP colon IP value. And we return no, there was no latest if there is nothing in Redis, right? Otherwise, we do a split, and we return the Perl hash containing the actual information. So the update is actually two operations, not just one, because we need to modify the current IP data, and then we need to insert that IP into a set for the circuit. Yeah, and of course it is a bug here, because I mean it's totally wrong the second line actually, because here there will be just a certain number, and the value will be just a not this kind of text.
Well, you need to add to the history too.
No, not at this stage. It's an update operation. We already found out, because we had the fetch, update, expire, and insert. So this is just the update operation. And insert is identical to update. It's only expiration which actually touches the history. So, and the expire latest, then we take the history for the IP, then we append it with a new line and insert it back. Then we get the history for the circuit number, append it and insert it back. And then we remove the IP from the circuit number current, and then we remove the IP key as well. So we actually touch all four types of keys here. Isn't it?
Do you always get something for X? I don't exactly understand when it happens. When somebody else wants that IP?
That happens when somebody else wants that IP, or when it is the same device but a bit too late. For example, it gets a list for half an hour, and then 1 hour later it asks again. It is given the same IP, but it's to this joint record, so we have to expire this one. Right. And so we got insert, update, and fetch latest, and that takes care of the indexing part. And now the querying part. The IP now is easy. We just do the fetch latest, and then say nothing is there if we cannot find the latest, and we still say nothing is active if the timestamp is not right. Because it is always possible that the thing expires and we don't notice, because there was no update for the same IP. Then it will still be in the current set, but it will not be current really, which is okay, because we can find out when we do the query. So the circuit now is a bit more complex, because we need to get all the IPs for that circuit, and then fetch in the loop information about that IP, and only return those IPs which feed the timestamp. It is still very, very fast. And the IP history is similar to the IP, because we take the historical data, which are guaranteed to be historical, and we get the current data, which just might be also historical if it's already expired. Then we join them together and filter by timestamps. And pretty much the same what we do for the circuit history. So we do the same thing as in the circuit now, and then we do the same thing as in IP history, but for the circuits. So the next step would be to estimate memory requirements. Yes?
Why do you need to clean up your outlet?
Just cut off the whole part of the history. Right. Yeah.
Can I just ask a question about that as well? I've noticed one thing that you've had a really big advantage here is you have a single writer, so you've got no locking constraints at all. There's only one process that's writing.
Yes.
But your history cleanup is going to be writing as well. How do you lock history updates happening while your history writer is?
I am going to. The thing is that I didn't write the history cleanup part because the application is running for less than a year.
Okay. Because that's going to.
So I only need to write that part in April.
Okay.
Right. Memory sizes. Since it is an in-memory store, it uses lots of pointers, lots of C pointers, so it actually pays to use the 32-bit Redis, unless your data size is, of course, more than 4 gigs, in which case you have to use 64-bit. But identical data sets takes substantially more memory on 64-bit otherwise. So how we estimated the data set for this particular task, we just dumped the whole Postgres database, and on the test box I inserted it into Redis using this schema I described, right? And then just look how much it takes, and okay, they're good for a year. Even if we do have some extra number of customers, hopefully, we still have enough memory to handle the task. Right, so I put around 700 megabytes for our database, which is not a lot. Quite manageable. So we can immediately, after having the indexer converted to Redis, we can immediately stop doing the indexing in Postgres for the switch over task. No problem with that, right? Because we will have the data in Redis. But unfortunately for the query, for a while we will have to actually do simultaneous queries for both Postgres and Redis, because we don't have a year worth of data in Redis, and it might not be a particularly good idea to try to import the historic data into Redis, because it doesn't take seconds, it takes a substantial amount of time. So the new data will come up, and how do we converge importing Postgres into Redis? One thing is to do it for estimating memory requirements, that's fine. But another thing to do it in production, it was actually easier to make the query, which is only 2 times a second, not 100 times a second, to query both Redis and Postgres at the same time for 1 week, right? So, but we even run 2 indexes in parallel to make sure that we didn't do the bad things to the logic, Redis, and comparing that the data are fine, and that we are getting back what we actually expect, comparing the results with the queries. Right. I think I already talked about this part. Right. And here's the result. So as you can see, sometime at the beginning of week 14, we stopped the Postgres indexing. So yeah, I mean, it's basically very, there's nothing to describe. The picture more or less self-explanatory.
Which machine was this? What task was it doing? Which machine was this? Which task was it performing? The indexer or?
That's the indexer machine. I mean, it had the database and it had the indexer process for the database, and now it has the indexer process for Redis.
So were you running both on that machine in that block beforehand, both the Redis and the Postgres on the same machine?
Well, actually, I think this part is Postgres only. And I think we run both Postgres and Redis indexer for about 1 week, no more than that. Right? And there is no more Postgres indexer. But query is still there, and it is still there after later, right? Yeah. But it doesn't. Now, I would like to go a little bit and talk about a completely different situation. Redis also supports a very simple publish-subscribe mechanism. And again, those of you who attended David's talk, he talked a little bit about that. So it is possible to send messages to whomever wants to receive those messages. And again, there are tons of solutions like that. The best one is probably ZeroMQ. But Redis, if you already have Redis, then it is pretty convenient to use that one if you need publish subscribe. So you could publish arbitrary messages, and then you can subscribe to a channel in a different process and basically wait for messages and do whatever it is with the messages you receive. You can subscribe to multiple channels using the normal wildcard thing. What about persistent queues? If you need a queue which with multiple processes putting stuff into a queue and some multiple workers taking stuff out of the queue and doing something with it. It is possible to emulate this feature with Redis because we cannot use publish and subscribe inside, but we could use the key expiration feature, which David talked a little bit about, and I didn't yet until now. So we could set the key with an expiry, and then after 3 seconds the key will be gone. I mean, after the specified expiry, which makes it pretty ideal for doing some work queue tasks. I mean, not that. Not really for the work queue, because for work queue you don't want to expire anything. You want to do the work. But there are some situations when when it is very, very useful to create a queue to make interested parties who come at a party a little bit later, so they cannot use the publish subscribe mechanism, because if they missed a message, then it's completely gone. But instead, to come and ask what has happened during the last 10 minutes, what has happened during the last 15 minutes, so that I could get a chance to do something. For this reason, the key expiration is very, very useful. And an example of it, which we also did at work, was for handling, for doing some special handling of transactions in RT, request chart. Because RT by itself does quite a lot, but sometimes there are situations when you really would like to be notified when something special happens, and you don't really want to go and modify the RT code itself. And sometimes the watcher, the custom scripts are a little bit too much, or not maybe very convenient, because you have to bring too much of your own custom code, which has nothing to do with it, right? So what we've done is we instrumented RT to put some little snippets of every transaction information into Redis. So the code is, I cannot show you the complete code because it's too large, but the idea is that it uses the increment to keep a custom sequence, and then it puts some JSON data structure about every RT transactions and sets it to expire within an hour. So after that, we created a small class which behaves like an iterator. So you can register yourself as a daemon who is interested in RT transactions. And then this class will maintain a little key in Redis saying when was the last time this particular daemon asked Redis about RT transactions and what was the latest transaction it actually processed. And then you iterate over all the new transactions. So you could easily put your little daemon into Cronjo and make sure that it will get the important stuff. So within that, you for example, can verify, whether there was a ticket created in any given queue and what was the subject, and maybe I need to do something special about it. And the usage is very, very trivial, as you can see. And how do we do that? The actual code, well, the constructor does nothing, really. Just remembers the daemon ID. And the iterator fetches everything first, unless it was already fetched. Fetches all the keys which match, which were created later after RT. After this particular daemon has queried RT the last time. And it gives back one by one. And this is the fetch itself. It uses this daemon ID here. And the commit updates the daemon ID with the last transaction processed. And I think this is about it. So there were basically two more or less unrelated tasks here. The bonus tasks are here. And do you have more questions? No more questions?
No question. Do you really think it was worth it? Did you need all that improvement in performance? The effort in development compared to buying 3 more servers, was that worth it?
Yes, definitely. Definitely. Because now we have substantially more room for scaling in the future. Right?
Yeah, servers are relatively cheap.
Yeah, yes and no. Yes?
Is there any reason why you store your history as a single string as a 6 or
hashes and sets are not free variables. So that would explode quite a bit the data set size.
True, but it would be a lot easier to
That is true. That is true. But again, I mean, we are talking like maybe 2.5 times larger data size.
I'll definitely support you on that. It's often better to have a dumb algorithm and a blob than a smart algorithm and a smart data structure. If you're updating it once a month, who cares?
Yeah.
In that sense, why couldn't you just use
what is in that persistence. The main reason not to use non-cache is persistence. All right. Thank you very much.